introduce the repairman, or the face of BBC Materials. Take your pick. Yeah. Mark is well known to most of you, I hope, and just going to let you talk on whatever you like.
Oh yeah, thanks very much. Yeah, and I think my talk.
I'll keep you to time.
Oh yeah, thank you very much. Yeah, I will definitely do that. Yes, thanks very much for the invite, and to be amongst sort of like-minded souls, it's really heartening, don't you find? You know, it's this sense of energy that we're all working together, and I think that is the way forward. Materials being so important. I'm going to talk now. We're going to dive into the details, but first of all, I'm going to just motivate the talk with the idea of what we mean by repair and why this piece of work I think is very relevant to that. So why is repair an important part of the puzzle? And we've already alluded to it with earlier talks. So you're sort of familiar with this circular economy diagram where we need to move from a linear economy where we're basically just sort of making stuff with fantastic stuff, getting stuff out of the ground, incredible material science. 20th century, basically that's the 20th century, and it's a huge achievement. But this is the bad bit, which is basically we put stuff in a hole in the ground or we burn it at the end of life. And the future is going to be that everything we have in the system, everything we have in the economy is recycled or reused or maintained or repaired or reduced. Now, what that means really is that 50% of the economy is going to be this, and 50% is going to be making stuff. And that's a huge shift in where profits come from, because this generally is not very profitable. And that's an enormous amount that's trillions of dollars are going to move that way this century. And so I guess that's one of our puzzles, is how do we make that profitable, because it's not profitable now. And I'll just give an example of the stuff that I've been working on. We've been running a project called the Big Repair Project, where we've been looking at this and going, well, look, if you look at the household items you have, all have metals like washing machines, toasters, kettles, your electronics, your smartphones, your computers. The average person has 30 of these, and they last not very long anymore. And they essentially are designed to be obsolete. They're designed to break and for you to buy a new one. And that's where the profit is. So the money is here. If you think, well, if you say, well, okay, we'll recycle them, it doesn't happen very much. The recyclability rates are tiny. And the reason for that is it's not profitable. By and large. And secondly, because this is the least good option, recycling, in terms of CO2 emissions. So in the next 20 to 30 years, to hit our targets, we cannot rely on recycling. Even if we could make it profitable, we don't have enough renewable energy to fuel that anywhere near. And we need to actually decarbonize the grid first anyway. So what we've got in the next 20 or 30 years is an opportunity to do something about global climate change in this area. Because this is actually... It's possible, because repair, making things last longer, if you make your toaster or your washing machine last longer, like by a factor of 2, you halve the CO2 emissions for that object in terms of its manufacturing end of life. If you make it last 5 times longer, you divide it by a fifth. You make it 10 times laster, you divide it by 10. So there are big opportunities here. But, as I said before, it's not profitable. And so the big companies have been trying to work out how to make money out of this. And what they've moved towards is models where they own the repair ecosystem. So Apple and John Deere tractors are good examples, where in America anyway, there's been enormous litigation. John Deere tractors, it used to be you buy a tractor, you're a farmer, you buy a tractor, you know how to repair it, you're often hundreds of miles away from your dealer. You're out in the Midwest. You're a total engineer, and also your family and all the people who work in your community. You can solve any problem. Until recently, until these tractors and machines that make our food so cheap and affordable, they've all been they've got software interfaces now, which means you can't actually repair them on site unless you have a John Deere repair person come to you or you go to them, and it's just not viable. And there's been whole-scale revolt in America about this business model, but you can see why they're doing it, because they want to make money out of repair. They can see the future. So there's this tension, right? Apple have done the same thing. All the smartphone manufacturers moved in about 2013-14 to stopping you changing the battery. Now, that's the one element you can guarantee would extend the life of your smartphone from 2 years, roughly, as it is now. That's when the battery starts to die. To, if you can repair it, you can have another 2 years, and then another 2 years, another 2 years. Everything else will last at least 10 years. The screen is the other thing that breaks, but you can again make that modular, allow people to repair that. But they've opposed all of those things. They locked the batteries in. They said it was unsafe. I mean, there's lots of doubts about that claim. It's basically not true. And you can see why they're doing it. They also see the future, right? They want to own the repair ecosystem. Now, there's been citizens uprising. There's been the right to repair movement, which is very big, very global. UK is big on it. America is big on it. Europe is very big on it. And that has finally given us some legislation, which is the tool we talked about this morning, which is the other bit of the puzzle, which is, okay, we want to level the playing field for all these companies. So the ones that are doing the right thing get rewarded. So essentially, right to repair legislation has come in, basically saying you need to make repair affordable, you need to make spare parts available, and you need to be able to kind of do it at a reasonable cost. Now, the legislation at the moment, it was brought in the EU 2021, in the UK 2021. It's very, very, very low-grade legislation in the sense it only covers 4 product categories: fridges, washing machines, TVs. It omits smartphones, which is tells you the power of lobbying, if you ask me. So what we've got is this big fight in the legislators. New York just passed their right to repair bill, New York State, not America in general. But Biden's been very pro it. He understands what's at stake here, and that this is the new economy. So there's lots bubbling up, right? But no one can quite solve the balance that we as a community can accept, which is how much are you going to pay to keep your smartphone for 10 years in terms of ongoing costs in terms of repair, and how much are you going to, or would you rather, and which is the current state of affairs, have disposable smartphones. But we know that that's a cost to the environment. We know that's just not a future we can all live in. So here we are in repair, right? We really need to make this work. It's about economics, it's about policy, but it's about materials. Okay, so this is the future as I see it, having painted that picture, which is consumerism's dead. I mean, it's still going like a zombie because it's the only thing. It's how we got here in the first place. It's how we got all this wealth, is that we actually learned to mass produce things, give stuff to them. And I mean, General Motors in the 1920s coined the phrase disposable obsolescence in order to get the economy going. I mean, the Americans were the first to really understand if you keep changing your products every few years, people will buy more, they'll feel good about themselves. That actually drives whole-scale efficiencies of mass production. And so it got us to this wealth. But of course, the terrible cost of that, which was flagged up in the 1970s, the 1980s, 1990s, all the way until now, it's finally the penny is dropping that the environment, climate change, but not just climate change, water usage, toxicity of the groundwater, use of pesticides, use of herbicides, use of fertilizers, all of these things are really we're causing a biodegradability crisis. So consumerism's got us here, but it's dead because it basically offsets everything to the environment. So we're going to be guardians of stuff. It's a new economy. We don't even know how it works. No one can make money out of it at the moment, pretty much. But that's an opportunity for us. Okay, now, we're material scientists, so we look at the world through scale and structure and properties. So our familiar scale diagram. And the thing is, we got to thinking when we're looking at the repair stuff, is that, we're sort of talking to companies and all these things. I love all that stuff. I'm really into it. Talking to the media, talking to the public about it. But actually, when you get down to it, it's interesting that there's a kind of different repair mentality in nature than in materials. And we were sort of digging around this world and thinking, well, what really is the difference? And just to sort of talk you through. So this is the living world over here: trees, whales, mice, hair, fleas on the hair on the fleas, intercellular, cellular, DNA. And the thing about the natural world is it makes things that fly, it makes things that can go fast, it makes things that can think, just like computers. It can make things that fall in love, in fact, which we can't do. But maybe we will be able to. Probably will. That's my ChatGPT fall in love with someone, I'm soon. It's amazing thing is that it's got two things that we can't do. One is that, the reason why these things all last long is not because they can be built, they're built from the ground upwards, but that we're constantly falling apart as organisms. Our metabolism mostly is about checking whether the things are where they are. Do our eyes work? Do our head? Is our heart beating? And if things have kind of deviated from homeostasis, trying to do something about it. And there are loads and loads of mechanisms at every single scale, checking the scale above, checking the scale below, and repair. Self-repair is our metabolism. So self-repair is constantly happening to keep things going. So they're dynamic. We make stuff, it's amazing, but then it just sits there, by and large. I mean, fans work on metal health summits. It's a brilliant idea, and I think that has a lot of corollaries to this. They also do something else. The recycling is inbuilt in the sense that all the building blocks are essentially, I mean, there are some notable exceptions, but nature basically recycles everything. I mean, there's obviously been hiatuses in that system, and that's why we have stocks of oil and coal, right? There was wholesale organisms which were not recycled, and now they became a mineral layer. But generally, that's a brilliant system. It's an amazing system. Now, we haven't done that, but this is, I think, the future. We're going to have to move towards self-repairing materials to keep things going for longer, but also to, of course, make the recycling a intrinsic part of the system. Now, we're not going to move away from mass production. Otherwise, we're all going to get poor very fast. And actually, that's the best way to use the resources, is to mass produce. So pretty much the production, I'm pretty sure, is going to stay as mass production. But repair is essentially a local thing. It happens in the object, in the product, in the material, or it happens in the local area, which is, someone comes to your house, or you take your car to the local, but you're not going to go very far. So what's interesting about repair is that it's sort of politically and socially different from mass production. Mass production has hollowed out communities across the world. It's caused all sorts of uprising and unrest, which we're seeing today. And actually, I think repair offers... So even though we're in the microstructure here, actually, there's a connection to our social lives, our political lives too, which I think is interesting. And we need to keep saying that as material scientists. It's a very human occupation. And the people will come in, the smart people will come into our industry when they hear us talking that way, right? When we're not just completely obsessed with technical details, which are interesting, which I'm interested in, but we have to constantly contextualize why we're doing this. Okay, so... Oh yeah, sorry, one thing to say. So essentially, the problem as I see it with trying to move to get to more repair and more recycling, which we haven't done very well on, is that our materials to get our properties have become more and more complex. And more, so for 50 or 60 elements we're using in smartphones, and we don't know how to get them back out again into the system cheaply or with low CO2 emissions or low water usage. We just don't know how to do it. It's just a totally unsolved problem. And yet we're wedded to that complexity because it gives us the smartphone, it gives us the airplanes, it gives us these incredibly efficient stuff. So you've got, in a sense, you can say, well, let's go really simple. And you see that around the place. People are sort of trying to simplify their lives. But I'm not really convinced that us as humans will ever sort of buy into the simple life, the good life. I feel like as humans, we have to sort of be more aspirational about this to drive people forward. So I think the future is going to be, we're going to have to grab complexity and we're going to have to do what nature does and get a lot more self-repair in there. So, not the whole future, but a lot of the future, I think, is going to be about redesigning materials to be more dynamic, to be self-repairing, and actually self-disassembling, because I think that probably is part of the problem of dealing with the complexity of materials. They fall apart, but they don't fall apart in an enormous vat or shredded. They actually separate themselves into parts, maybe modular parts. And there's this sort of term, animate materials, that we kind of came up with, and I say we, it's a whole we had a whole conversation in sort of 2019, 20, 21 at the Royal Society about this topic. And in the end, there are lots of terms for this: smart materials, active materials, programmable materials. I'm not wedded to any one of them, but in that way, we talked about animate materials. Okay, so don't be hung up on the word. But essentially, I think it is a kind of a natural progression. So we saw this before too. Like if you look at the past, we know we did Stone Age, and we actually made textiles and glue and woods and ceramics and metals, and we've moved forward in time, and we've got to things like energy harvesting materials, which have to be part of this problem, right? If you're going to have a dynamic material, it needs to get its energy from somewhere, and we've got these. These are solar cells and acoustic harvesting devices and so on. And we've got other things which I'm going to talk about now, which are baby steps, as I see it. I'm just trying to get you interested. And the other area, which I think is an alternative future actually, and you see it a lot in material science, is that actually we go the biology route and we basically use the cell as our building block for most things. Nature does it, works pretty well for nature. Could be the future of a lot of our technology. And in fact, it might not be either or either, right? It's probably going to be both. So stuff in the body, biology, stuff that's sort of soft might be biology, and stuff that's hard and high temperature might be self-repairing stuff. Anyway, that's That's a lot of preamble. And there's just one more piece. Okay, how do we talk about these materials? What do they need to have? So down here, I've got 3 axes. It's not a very good diagram. I apologize. It was better than the previous one. So down here is we've got adaptivity, we've got activity, and we've got autonomous. So active means you can change shape, or you can change material. You can get stuff in, you can swap stuff out. Adaptive means you can sense. You can sense when that needs to happen. You can sense your environment. You can sense what's happening around you. So we've got sensing, we've got being able to change and make things happen. This sort of actuation, really. And autonomous means you can compute. You can compute the course of action. So you get some messages in, you compute the action, and you do it, right? Now, as I see it, pretty much all the materials we use at the moment are low on every one of those scales. They don't do any of that stuff. I mean, they do some of it. That's why it's not completely at zero there. And we've made smart materials and so on. But as we move towards where nature is, now nature can do all of that. If you think of a tree, it can work out that it needs more water, or it's a drought. It'll start to drop its leaves. It will start to curl up. So it can sense, it can do things, and it can compute. So a tree, that's the material of the future, right? A tree. Maybe not an arm yet, but a tree. Can we get there? Well, that's the direction of travel as I see it. And we already have self-repairing materials. They're very sort of rudimentary at the moment. And I want to just take you on a journey to the next level, what I'm calling linkage fabrics. Okay, right. So what are linkage fabrics? Okay, how are we doing? All right, I'm going to run through this already. So this is obviously Monty Python, and they are not wearing chainmail. They are wearing woolen imitations of chainmail because they were arts graduates and they couldn't possibly have the physical fitness to actually wear chainmail, which is extremely heavy. And anyway, it makes more sense. It's much cheaper and funnier. But this was the revolutionary materials time. It was, for thousands of years, this was the armor. And why does it work so well? Well, because it's actually a fabric. It can mold to your body. It can be shaped to your body. You can move around. It's flexible. But it's actually got a lot of the strength and toughness of a monolithic metal steel. So it's got topological elements, and if anyone's interested in these, I'll go into them later. But basically, the topology is really key here, because what you've got here is a modular material. And I think that's one of the key aspects of the cellular world that we need to imitate. What nature does is it has cells, and they do the sensing at that scale. They do the changing shape. So they grow, they change shape, or they die. And they also do the computation. So inside the cell's DNA, and DNA is a great computational tool. In here, what you see are cells, right? As I see it, right? Now, the fact that the chainmail doesn't matter to me, and you'll see in the next slide, that's not really the point. The point is that they are units of the material that may have autonomy, or you can give them autonomy. So now you can have you can actually do it these days, because 3D printing, the complexity comes for free. So you can make them into things that actually are completely, like this is like a track, and each one of these is one of those links, and they all interlink with each other. Now this link is an individual link. Now if that link can change shape, can compute, and can sense, you have a material that is animate. How do we? Well, if we start off simulating them, I'm not going to dwell on this, but we're basically looking at trying to make sure that we understand how the links connect to each other, how they stop going through each other, maintain topology, and how they communicate and change shape. And we can do it, and you can make anything. It turns out it's kind of fun. There is no limit to it, and you can work it out. But just the things you can program into it are really cool, even when you don't have actuation. So if you just design the links like this, so the bottom of the link here is bigger than the top of the link, and the bottom of the link exactly equals that length, exactly equals the interlink distance, then if you flip that chainmail up one side, it's completely stiff, right? Because these can't move past each other on the bottom layer, right? But you turn it over and it's completely flexible, and that's just cool. But it could do it automatically, right? So here's another example of that. So we 3D printed these. This is the simulation, and this is the physical thing. So it works, and you can play around with this in all sorts of ways. But basically, it just means you can do graded properties any way you like. But I think the important thing about this is that instead of thinking of materials monolithically, which we do, we're sort of continuous metallurgists. If you break them up into these lumps, right, you can then have different properties per lump, and you can get them to change shape in the simulation automatically. So how would you actually do it in physical reality? So first of all, one thing you can say is you don't really need to worry about the complexity of the individual links and how they interact, because actually with 3D printing now you could do that, and we're doing it. You can kind of cover that complexity. So you can have all sorts of interlinking ways of rotation and shear and screwing in and out, and that doesn't really matter, and that all works. You can also use our computational tool to back calculate what you want some of the material to be doing and other materials not. So basically this is a diagram where we've got a material that's going to be an actuator, and it's only going to actuate to this knee. So it's going to change this leg of this building or this car or whatever, this airplane, and it's going to allow that movement. So you basically map the strain of the linkage fabric around this, the structural component, and then you back calculate the strain for each of these links that needs to happen in order to do that change from there to there. And then you program that into the material digitally, and then you print it out, and lo and behold, you get your answer. It will only do work because you're programming all the physical interlinkages and all the things that can and can't happen. Again, this is very fast but essentially, okay. So how do you get them to actually actuate? Difficult. One of the technologies we used, which we fell in love with, was that if you 3D print materials very porous, you can actually use the porosity. Actually, powder metallurgy gives you the porosity. You can then put in magnetic nanoparticles through a liquid process afterwards, which we did, basically dunk it in some liquid, ferrofluid. So you have nanoparticles down here, and you have them inside each one of these links, and then you have the whole linkage structure. And now you can use magnetic fields to basically either actuate them all simultaneously, in which case it goes from this to this, or you unactuate it, in which case it goes from that to that. So it works, but there's the experiment. But the good thing is, it works. The bad thing is, magnetic fields are just a pain, and it's really difficult to control them, and you can't really control them link by link, and so on. Anyway, proof of concept of something. Now let's make each individual link activated by an electric field by putting shape memory alloys in. Yes, the metallurgists have always been looking for a good application of shape memory alloys, except for kettles. Let's do this. Will this simulation work? I'm not going to tell you about all this stuff. I just want to see if the simulation is going to work. Yes, okay, so that's the simulation. So they're all loose, and then you actuate them by changing the link, just the link geometry. So you're basically shortening one of the links. They're all doing the same thing, and you get this actuation. And now let's do. So forgive me to a metallurgist audience. So the 3D printed links are in PLA. I'm really sorry about that. But inside each one of those is a shape memory alloy actuator, all linked up, all electronically linked. And is this going to work? Oh, yeah, that's to show you it's all flexible. It's not a trick. And then turn on 12 volts, and you get that. Okay. Inspiring. It's very baby steps, but that's fully stiff. Okay, and then it'll go back. Yeah, I know. It can be all sorts of embarrassing things. Let's not dwell on those. So we've run out of time, but looking ahead, I can see really big applications for all these types of materials where we basically embrace complexity. We get things to last for longer, and what we do is we program into them their ability to actuate, to sense. But crucially, what we do is we start thinking of material structures as cellular, modular, in the way they interact with each other. And that's the key thing. And then you can get self-repair, because we've done the simulations, and if one of those links dies, you can get all the other links to compensate for it. So it'll still do the same overall actuation, but now they've learned that one of the links died in it's an airplane or it's a car, and it's worked out that a couple of them have died, but it's still doing what it should be doing because it's computing the answer. And we can get them to self-disassemble, because we can actually have a thing where you press a button and the voltage goes up and all the links fall apart. So it's, again, baby steps. I'm not trying to make too much out of this, but I sort of feel like we need to do two things as a material scientist. We need to have new solutions that really are going to address longevity, so making things last for longer, self-repair, self-disassembly, as well as interacting on policy and supply chains and of the monolithic materials. We're not going to do either or. It's going to be both. If you want to look more about animate materials, we did publish this, the scoping of the whole idea, and it's a free download from the Royal Society. Just search animate materials Royal Society. This, if you remember anything from today, I think this is something we have to just agree on. Like, consumerism is dead. It's going to be exciting coming up with the next thing. What are we going to call it? That would be good. And credits and thank you. And I'll talk to questions. Yeah.
Thanks, Mark. Amazing as usual. Any questions?
That's a very interesting talk. In your taxonomy, I'm a little surprised, Mark, that you didn't use the term metamaterials.
Yeah.
Now, the physicists have been working on metamaterials for quite a long time with remarkable successes, things like invisible cloaks and things of that ilk. I won't go into the range of them, but it seems that what you've been describing is a class of metamaterials.
Yeah, I think that's true. They are a class of metamaterials, and they're in the structural domain. And in fact, there's a whole lot of people who've been doing property gradients in terms of elasticity in metamaterials. And I agree. And the names proliferate, don't they? But I think there is something about the fact that they're active, that animate, and the idea of modularity that I think is slightly different. So give it that flavour.
Another question?
Very interesting, very inspiring. I have a question, however. Thank you. I wonder, your design is based to go through the closure loop, which is the reuse, starting from your initial model. But, building on complexity, as you said, I wonder at the end if we make more difficult the recycling at some point, if we need to go through the recycling cycle at the end of the life.
Yeah, I think that's a fair comment, and I think I think it's not either or. I just think there are some things that are always going to be complex to get the properties we want, and this is a way to think about how to make them last longer. At the moment, I'm just going to go to I think the thing is here, right? Recycling, in a way, is benefited by simplicity of material. So you can see monolithic steels and aluminium and other things going through this route once we can decarbonize things. I don't see them going away. That's a big problem to solve. But when you think about a nuclear reactor or things that you just don't want to get in there, you don't want it to have to be recycled. Actually, you want it to last for a long, long time. I think there's a really interesting opportunity in places like nuclear, which are going to grow, right? Which is that the energy is the fast neutrons. Can you use the energy to get the material to constantly, reorganize itself? So looking at energy fluxes and understanding the areas, not all of the areas, where complexity is unavoidable, but actually it's not good enough just to put complexity in there and say, oh, well, we can't recycle it, or we don't know what to do with it, we'll just put it in a pile. I think this is where this comes in.
Going to be short.
Oh.
I was only going to make a comment anyway, but Mark can respond if he wants. I was only going to make a comment, and so you can respond if you want, Mark. What I wanted to say was I'm completely in agreement with you about the complexity issue, which was just mentioned. I wanted to make that comment anyway before the last question. So there is a big strand in the climate problem community which says, make everything simple, go back to living with nature and everything, and if only it was so easy. Not that that's easy, but I think there's absolutely no chance of that happening. The amount to which the Industrial Revolution has caused massive problems, and we're seeing what those problems are, as you rightly said. But they've taken millions of people, billions actually, out of poverty and starvation existence and put them into wealth. And it's not at the expense of the others. The others are living pretty much the same as they were before. So, it's not that others have suffered, but we've not got to prevent them from doing it. We can't all go back to that. So I'm absolutely in favour of complexity, and that is a massive technological, scientific challenge to us to change the science and technology. I just wanted to say that's our problem, and we can, and if you accept that complexity is going back to nature is not the answer, science and technology has to provide a lot of the solution. And so working with complexity to find answers, as you've done, is exactly the right way to go. That's not necessarily exactly the solution, but doing that kind of thing is the right way to go. That's all I wanted to say.
Yeah, I mean, I agree. And just to say about this work, I constantly scratch my head about, okay, but give me an actual application where that would actually work. And I sort of think it's too early. Like, we should be playing in that space. We really need to play in that space, because out of play, coming back to your point earlier about, like, make the stuff. When you make it, and you get people involved in just the idea, like, make a self-repairing material. Wow, people get excited.
Let
and
me
I think
another very quick comment on that, Mark. Please, just as a response, and we've heard it in Duran's talk, in other talks. We've got to get back to the notion of experimental scientists who play, who discover. Discovery. The scientific revolution occurred in the 16th century with the notion of discovery. Discovery is what initiated science. And we're in danger of losing it, largely because of computation. Everyone thinks, you just bung it in a computer, it'll tell you the answer. Well, Aristotle didn't give us the answer before the scientific revolution because he was wrong with all sorts of stuff which seemed obvious, and the computer ain't going to give us the answer because they'll tell us lots of stuff that's wrong.
Yeah, and coming back, we're just one thing on the educational thing. So we talked about education again, and but actually it brings it in, because if you get people fired up about repairing their own stuff and the fact they can't do it, and what's the future? What's the solution? I see it with my own kids. I see it with our repair cafes which we run at UCL. People, it fires them up, and then they want to solve that problem, and that's what you need to do.
Great. All I need to do is just thank our three excellent speakers.